For the introduction. So good morning to everyone, or good afternoon or evening, depending on where you are physically located. My name is Waylin, and I'm here together with my colleagues, Doug, and both of us are the software engineer at Graphcore. So today we are going to discuss a software emulated layer that we developed at Graphcore named IPU over Fabrics. It's a software layer that is highly coupled with the RDMA technology that is familiar in this community. So let's get started. So this will be the agenda that we're going to cover today. First, we will briefly introduce the Graphcore IPU and also cover the current generations of the IPU platforms with the codename BO M2000. Then we'll move on to the main topics where we discuss about what is IPU Fabric and why we develop IPU Fabrics. And then we'll move on to the heterogeneous memory on how do we register a various memory subsystem on a complex system that contains multiple memory subsystems. And then we go into the data flow in details, and then we will conclude the talk. So I'll move on to Doug, that he will go through the presentation of the first two sections.
Yeah. Sorry. I'll start with an introduction of the Graphcore IPU, the Intelligence Processing Unit. That's a processor that we have developed in-house from ground up, and it's mainly targeted at machine learning and AI acceleration. As you can see, it consists of 1,472 independent CPU tiles.
Sorry.
Yeah. We can view them as sort of small cores. And an important part is that they have memory. They have their own SRAM memory. Each of them has also 6 worker threads. So that gives a total of 8,800 fully independent programs we can execute in parallel per IPU. It has a aggregated static memory of approximately 900 megabytes per second, and a total of 65 terabytes per second memory bandwidth per IPU, and that's due to the SRAM being close to the processor cores. As you can see in the middle, there's the IPU exchange crossbar. That's a trunk router that supports 11 terabyte all-to-all non-blocking exchange. The chip also has a PCIe Gen 4 6NX host interface, and we have the IPU links, 10 of them, which has 320 gigabyte per second chip bandwidth. And in case you guess that they are implemented as PCIe Gen 4 8X interface. So move on to next slide. So to use this highly parallel processor as easily as possible, we are using a parallel model that's called bulk synchronous parallel. That breaks the computing down to 3 distinct phases: a compute phase, a sync phase, and an exchange phase. So in the computing phase, then all the memory that's used is residing at local memory to the core, and that allows that we have fully parallel independent compute, and the processing can be load balanced between the available cores to ensure that they all complete as much as possible in the same time. After that, we have a sync phase where all all cores sync up, and having sort of a separate phase for that ensures that there's no data contention, erases, deadlocks, or live locks. And after that, there's an exchange phase where the data is moved and copied to where it needs to be for the next computing phase. So now that we have talked about the IPU processor, we can talk about the platform that we have for this current generation. It's called the BAU M2000. As you can see, it has 4 BAU IPUs, which together more than 5,000 processor cores and 3,500 parallel threads. This gives a compute of 1.5 petaflop, 16-bit compute. So in addition, as you can see in the middle there, we have the gateway that has its own SRAM memory. No, it's DRAM memory, sorry, which we call the streaming memory. It has 128 GB of that. And in addition, it has a gateway links that has 100 gigabit Ethernet interface. We use a proprietary Ethernet interface for that. And as you can see in the bottom there, you see the RNIC, which provides the link to the host. So now that we have seen the platform, we can move to the main topic of this talk, which is the IPUoF Fabric software. I'll begin with explaining look a little bit at the architecture. We see the Poplar framework in the middle there, and that's the software that glues the ML frameworks with the M2000 systems. And we see that the IPUoF Fabric can be seen as a device driver that's attaching Poplar to the M2000. So we can also view that as a PCIe, as it replaces the PCIe host link to link the pod systems over Fabric. So now we have seen where the IPUoF resides. We can zoom into the software stack within IPUoF Fabric. IPUoF Fabric is a pure software layer. It's all in user space currently. And its functionality is to establish and discover remote devices and to perform data movement, that is feeding data from the host where the ML framework is running and onto the IPU, and fetching data from the IPU back to the host. It's a simple client-server user space application, and it's written over RDMA verbs. It uses the CM to establish the connection. We also have a gRPC service for things that are non-performance critical. Other than that, on the server side, the server resides on the M2000, by the way. We have also have the PCIe driver, which we use to perform the actual operations on the IPU. So yeah, on the next slide, yeah, there we have another diagram. This is more to sort of emphasize the purpose of the IPUoF fabrics. So the idea is that we disaggregate the IPUs from the host. If we had locally attached IPUs, we would have to scale, so that would be connected to the PCIe slot or the switch on the host system. Then we would have to scale the normal compute on the host with the IPM, with the IPUs. But with the disaggregation, we can support different requirements of graph computations. So we are more flexible way. Yeah. And I'll leave it over to Weilin to talk about heterogeneous memory.
Yeah, as Doug mentioned, I mean, one of the key functionality of IPUoF is to transfer data from host to the BAU M2000 platforms. So in this system, we basically discuss how IPUoF able to perform data feeding and fetchings to and from the IPU. So as most of you know that most of the system today usually consists of a combination of various components such as FPGA, accelerator, and various memory controller, and etc. And there's no exception in our BAU M2000 platforms. So our BAU M2000 platform has a in-house built DDR controller resided inside the IPU gateway, mainly to provide a fast path from this BAU M2000 platform to the IPU device. So we name it as a streaming memory. So on top of that, as Doug mentioned, every single IPU has its own static memory, or we call it the tiles memory, which is located tightly or closely to every single core. So on top of that, we also have a DDR, which is bundled together with the SoC inside the IPU gateway, where we use it as a non-performance critical or management operations. So how can actually the software frameworks, I mean, pipeline scenario actually feed data to different memory regions pinned to different memory subsystems? So with the BSP model, as what been discussed by Doug, so the Graphcore Poplar, we call it as a graph compiler, actually using a compile in communications, which means that all the host IO traffic pattern is actually known, and the selections of the memory to use, either you want to land it directly into the streaming memory or to the tiles memory, is transparent to the application users. So it will be selected anoxically by Poplar or our graph compilers, and depends on the size that the application needed. The Poplar will choose the correct buffer, and then he will inform or trigger IPUoF to pin or register the memory region correctly, so that IPUoF able to perform RDMA read and write during runtime. So from the low-level software perspective, so in this platform, memory is not just a memory, because we could not populate the streaming memory to the Linux memory subsystem pool, because we want it to be used for dedicated purposes. So we create a simple device driver to allocate the streaming memory, started with a simple mmap. However, we hit into the first challenge where remap BFN range isn't compatible with IPv rec MR. So thanks to this community, the discussions on the Linux RDMA mailing list, someone actually facing the same problems, and they come up with the solutions. So we are using the same solution where we create a no page mmap. And of course, we need to put those streaming memory into reserved memory so that we can allocate it with our device driver. And we need to provide a page fault callback so that we can insert the correct BFN to the VMA data structures when pinning actually happens. So now we look into the every single use cases, how do we transfer data to and flow from the IPU. So first we look into the host to device data path via a streaming memory. And again, with the assumptions that the communication has been compiled, so the host IO data path is actually known. So during the compilations, Poplar or the graph compiler in this case, able to know the size of the communication buffer, and then he'll inform the IPUoF to register or pin the RDMA memory regions. And as you can see that there are two identical buffer or two buffers in this diagram that we call it local MR or remote MR. And those are actually a mirror buffer, which identical size. So the reason is to pin those one on the host so that we can kind of transfer it over to the BAO M2000s. And again, how do we implement this? So as I mentioned, we use the no page mmap and just trigger the page callback once RDMA calling IBVREC MR. Then we pin the correct BFN to the VMA data structures. And as you can see, the flow is actually the application will copy the data. I mean, once the compilation is completed during runtime, the application will copy the data into or pass the data into the local MR, and then that triggers IPUoF to do a RDMA write. And then when the send completion come back or receive completion, depending we're using RDMA write or RDMA write immediate, then the IPUoF will increment atomic counters in the IPU registers to inform that he can move on to the next phase in the next program in the program sequence. So when this information is passed on and IPU read the same information, he realized that the data has landed into remote MR. Then he starts performs the PCIE memory read to retrieve the data into the IPU task memory. So one thing I'd like to emphasize here that as you can see that there's always an additional hops, which means that we're using the streaming memory as a bounce buffer. So you might question about in terms of the performance. So again, I'd like to emphasize that we are using compiling communications. It means that the host IO can be, the latency can be hidden by doing some smart optimizations, such as doing prefetching or lazy output fetching, so that we doesn't be blocked by these host IO with an additional hops when we're doing RDMA operations. So now we move on to the other direction, which is device to host. And again, it's the same process that we need two phases where during compilations, we create the communication buffer, which eventually is memory regions from IPUoF perspective. So when that's actually done, the flow is that IPU will write the data into the remote MR, and then he notify the or increment or decrement the atomic counters, and that will be notified to the host. And when that is informed, either the host can poll for a certain IP register, or there's a interrupts notified to the host, then the host will initiate an RDMA read to retrieve data back to local MR. And when the send completion come back, then we push the data back to the Poplar frameworks. The other data flow that we'd like to mention next is somehow experimental, means that we allow to push data directly into the task memory. So it's similar to the streaming memory. So during registration, two identical buffer is actually created. The only difference here is that the remote buffer is the device memory resided in the DDR. So we reside in the task memory. So the task of the IPU actually expose the task memory as a bar. So it means that we can pin it as a peer-to-peer memory regions. So when implementing the peer-to-peer operation, we realized that from the RDMA stack, there are two paths going forward. One is actually the pure directs, which is a non-upstream solution provided by NVIDIA or Mellanox. And the other one is the DMA buff solution that presented in the last all of our workshops. So we'll be interested to know what's the plan or strategy moving forward. So we'll be really interested to discuss with anybody in this community. Then this is the diagram that I'm basically just doing abstractions from the ML application perspective, that you created various tensor, and this tensor will eventually map to the tiles within the IPU. And then in order to stream those data into these tiles, so the popular compiler will automatically choose what is the most optimal path to move data into IPU, either using the DDR or using RMA write direct, which means direct into the tiles memory. And that's conclude our talk. So there are two key takeaways that I'd like to emphasize here. So what is actually what is IPUoF fabrics? So it's basically just a software emulated layers that supposedly, it should work across different fabric technology. And today we are implemented with the RMA or operate on top of Rocky. And why we need IPUoF fabric? And the key motivation is to provide desegregation of the IPU processing pool from the host processing, which means that we can scale the number of IPU independent of the number of hosts. And the functionality of IPUoF is basically do a data mover, means that move the data from the host into the Bow M2000, as well as discover the remote devices. So we didn't present any performance number from the ML perspective. So there's a kind of results very comprehensive results performed by our colleagues here in Graphcore. The result is published on our website, so including various performance number of BERT, ResNet, or efficient nets, and etc. So you can see that how IPU can help in improving some of these ML applications. Again, I would like to say thanks or kudos to the RMA community, where we actually implement the IPUoF fabrics, and with all the heterogeneous memory, like registering peer-to-peer and using streaming memory without any changes on the RMA stack. So that's it for our talk. Thank you.
Okay, thank you very much, both of you. We did have I'm just getting an echo somewhere. We did have a comment from Raghu on DMF support, DMA buff support that is merged into the subsystem, and now there's an explicit verbs app that can program that you can program too. Raghu says you could implement a Graphcore exporter with relevant popular API support. I apologize for the echo I'm getting.
Yeah, I guess that's the question that also whether we should go for the pure direct non-source. It seems like the suggestion is to use the DMA buff MR. So thank you, Roger.
Are there any other questions or input? Okay, thank you very much. We will be taking a break until 10 a.m. Pacific, so about 40 minutes or so from now.